Satellite. A satellite is a body which is revolving continuously in an orbit around a comparatively much larger body. Satellite कोई भी बॉडी जो रिवॉल्व करता है अपने से ज़्यादा लार्जर मास वाली बॉडी या लार्जर साइज वाली बॉडी के अराउंड, वो सैटेलाइट कहलाता है. फॉर एग्जांपल, अर्थ इज़ अ सैटेलाइट ऑफ सन. ईच प्लैनेट इन द सोलर सिस्टम is a satellite of sun. Moon is a satellite of earth. Other planets also are having many moons or satellite. Now we'll see principle of launching a satellite. For this we are considering here a very high hypothetical tower on the surface of earth whose height is more than the height of the earth's surface, earth's atmospheric surface. Look at here. This is earth and this is the radius of earth. We are just assuming here a tower which is having the height more than the height of the atmosphere. It is hypothetical completely. It is not real. But we are assuming here. Now let a body be projected from top of this tower. So a body is placed here which is projected from the top of this tower with some horizontal speed. This is the horizontal speed here, you can see that. Okay, so with the horizontal speed, and the body will describe a parabolic path under the effect of gravity. Always it happen, means you know that if we are just throwing the body horizontally here, so you have learned the two type of projectile motion, in which you have learned if a body is projected from some height, it is also attending a parabolic path which is called trajectory, and it will return to the earth's surface. Okay, and depends on this horizontal range. You can see that in first case the horizontal range is from this tower to A1, so it will touch to the ground at point A1. Now if the initial horizontal speed of the projection of body is increased, you will find it will touch to the A2. Gradually again the velocity will increase, so it will touch to A3 here. Okay, now what you will find here, as the velocity, the horizontal velocity by which the body is projected is increasing, the horizontal range also increasing. Initially it was from this tower to A1, then tower to A2, then tower to A3. So gradually the horizontal range also will increase. Now on, if you will see that the body will hit the surface of the earth at point A1, A2, then A3 as the velocity increases. Further, if we go on increasing the initial horizontal speed of the projection of the body, its horizontal range will also increase, and finally a stage will come. You will see that this is stage. Finally a stage will come when the body will not hit the earth's surface but will always be in a state of a free fall under gravity and attempt to fall to earth and become a satellite of earth. In this situation you will see that as we are increasing the velocity, horizontal velocity or the horizontal speed, this time the parabolic path will be like this, but it will not hit to the surface of earth, and it will just means it will in free fall condition always attending or trying to touch the surface of earth, but it will not try because the equilibrium, because it will be in equilibrium, it will continuously move on this orbit or set on this orbit around the earth's surface. Okay, so this way, this is the principle of the principle of launching of satellite. And for this, the tower means you can see that, as I told you, it is a hypothetical tower, means this much height is not there, means not possible. So just to keep this height or just to attain this height, we are using the rocket, and the rocket is initially it is moving vertically upward direction just by following the Newton's third law of motion or the law of conservation of linear momentum. So in that situation you will find when the rocket will attain this much height, it will just tilted 90-degree angle and projected the body to this horizontal, means projected the body to this horizontal um, way, means horizontally, and in that case you will find that body will be setting, or the satellite will be setting in this orbit. Okay, so this is the principle of launching of satellite. We have seen here the object or the satellite which is projected, the horizontal velocity as we are increasing, so we'll find that it will set into the orbit. So the minimum speed required to put the satellite into given orbit around Earth is called orbital speed of the satellite, and the value of orbital speed is different for the different orbit around Earth. For example, you will see here this is the Earth and the radius of Earth is r, the mass of the Earth is capital M, and you will see from the Earth's surface some height h. We are setting this satellite which is having mass m, small m, and this is the height h. The radius of the orbit from the center of the Earth is r. That means the small r is equal to r plus h here. Now we'll see in equilibrium the gravitational pull provided the required centripetal force to the satellite to keep it in its orbit. Whatever the gravitational pull is there of Earth on the satellite, that will provide the centripetal force to the satellite to keep moving on to this orbit. Okay, so that means the centripetal force must be equal to the gravitational force on the satellite. Centripetal force is the mv square upon r, because VO, we are representing the orbital velocity or the minimum velocity which is required to set the satellite into the orbit. So here the required centripetal force is mvo, that means mvo square upon r, and that is balanced by the gravitational force, or the gravitational force or the pull will provide the centripetal force. So gravitational force between the Earth and the satellite, that is gmm upon r square, where r is the radius of the orbit around the Earth. So this is gmm upon r square. This mm would be cancelled, so vo will come root of gm upon r. We know that the gm is equal to gr square by this formula. So in place of gm we can write here gr square. So this is vo is equal to root of gr square upon r. R is in square form, it will come out, square and root will be cancelled, that is r root of g upon r. So we will use either this formula, that is orbital velocity. We can use this formula, that is vo equal to root of gm upon r, or we can use this formula also, vo is equal to r root of g upon r, or we can represent here this r is actually r plus h. So vo is equal to r root of g upon r plus h. So this way we will represent the formula. Okay, this is the root, vo equal to root of gm upon r plus h. So all this four formula, that is 1 2 3 4, any we can use as the requirement. Now the important point regarding the orbital velocity, that it is clear from this formula that orbital speed of a satellite is independent of the mass of the satellite. In any of the formula you can see that there is no proportion of the orbital velocity, there is no means the direct or the inverse proportion of the mass from the orbital velocity. Okay, so there is no relation. That means it is independent. The orbital velocity is independent of the mass of the satellite. It will not depend on the mass of the satellite. And the orbital velocity decrease with an increase in the radius of the orbit, because you can see that the VO is inverse proportion of this root r. So as the radius will increase, the radius of the orbit will increase, the orbital velocity will decrease. So in the height of the satellite from Earth's surface. Okay, now depends, third point is that it depends upon the mass and radius of Earth. You can see here VO is equal to root of gm, so it depends on the mass, and here also you will see r, so it depends on the radius of Earth. So the orbital velocity will depend on the mass and radius of Earth, but it will not depend on the mass of the satellite. Next is the direction of orbital speed of satellite at an instant is along the tangent to the orbital path of satellite at that point. You will see here, as for the uniform circular motion we are looking, the speed can be given by the tangent at any point. So at any point in this orbit, if you draw any tangent, that will represent the direction of the velocity of, or direction of the velocity of the this orbital speed or the orbital velocity. Okay, next we'll see, when a satellite is orbiting very close to the surface of Earth, very close, that means h is, the height is very less than the radius of Earth. In this figure you will find this is the radius and this is the height. So if it is very close, this orbit is very close to the radius of Earth, almost you can say that h is very less than r, or the r and this r, the capital R and the small r, both will be almost equal. The capital R is the radius of the Earth and small r is the radius of the orbit. Both are almost equal because h is very less. Okay, so in that case the small r we can write as r plus h, and we can means equate with the r, capital R. These are almost equal. So in this formula of the orbital velocity VO equal to r root of g upon r plus h, we can omit h, because r plus h we can write as r. R plus h is small r, that can be written as capital R. So here we will write simply capital R. So when we simplify it, we'll find root of gr. That means the orbital velocity is equal to root of gr, and we'll put the value of g, that is 9.8, and r as the 6.4 into 10 to the power 6. So we'll find the orbital velocity of any satellite which is very close to the Earth's surface is equal to 7.92 into 10 to the power 3 meter per second, or we can represent in the kilometer also, that is 7.92 kilometer per second. Next we'll see, in case of satellite, the time period of satellite. Time period is, means it is the time taken by satellite to complete one revolution around Earth, and it is denoted by capital T. And we know that the formula for the capital T time period, time is equal to distance upon speed. Distance is what? Distance is the you can say the distance in one revolution, that is 2 pi r. R is the orbital velocity, sorry, r is the radius of the orbit of the satellite, and VO is the orbital velocity. Okay, so T is equal to 2 pi r upon VO. Now we'll put the value of VO, that is the orbital velocity, the formula which we have derived. T is equal to 2 pi r. In place of VO we can write here as VO is r root of g upon r. This value if we'll put, this is r root of r upon g. Now you will see that this T is equal to 2 pi. This r is, if we are keeping this inside, it will become square, and the square, the 2 plus 1, the exponent will add up. 2 plus 1 is 3 here, so r cube. So 2 pi upon r root of r cube upon g, and this is the formula for the time period of satellite, that this is T equal to 2 pi r upon r plus h, because small r is r plus h cube upon g, root of r plus h cube upon g. Okay, now for the time period of revolution of satellites depend only upon its height. You will see that for the Earth's surface r is fixed, g is fixed, 2 pi is fixed. So T, you can find that it is direct proportion of the h to the power 3 upon 2, you can say. So it depends on the height, by what height or from the earth surface up to which height we are setting the satellite. So period of revolution of satellites depend only upon its height above the earth's surface, and the larger is the height of satellite above the surface of earth, greater will be its period of revolution. Okay, now the second thing we'll see, if the satellite orbiting very close to the surface of earth, that means once again we'll see the same condition, that h is very very less than r, or s plus r, h plus r we can consider as capital R only. So if we'll replace the, in place of h plus r with r, you will find t is equal to 2 pi upon r root of r plus h cube upon g. So this will be r plus h, we can write as r cube. When we simplify, it will come t is equal to 2 pi root of r upon g, and we'll put the value of r 6.4 into 10 to the power 6 meter, g 9.8 meter per second square. Then we'll get here t is equal to 5.08 into 10 to the power 3 second, or 84.6 minutes. That means a satellite which is launched very close to the earth's surface, the time period of that satellite would be 84.6 minutes. Now altitude or height of satellite above the surface of earth. In this formula, the formula for the time period which we have derived, this is t is equal to 2 pi r root of r plus h cube upon g. From this formula only we will simplify, we'll take the square of right hand side and the left hand side, so it will become t square equal to 4 pi square upon r square, and this is r plus h cube upon g. We'll leave r plus h cube here, or we can just transfer r plus h cube this side, the left hand side, and t square will place in the right hand side. So we'll find r plus h cube equal to t square r square g upon 4 pi square, or r plus h will just take the cube root both the side, the left hand side and the right side, so it will be free from the exponents, that is r plus h, and this is t square r square g upon 4 pi square root of 1 upon 3. So here you will see that if we'll just take r this side, so h will be equal to t square r square g upon 4 pi square to the power 1 upon 3 minus r. Momentum of the satellite, we know that the angular momentum L is equal to, if we just check the magnitude, it is equal to mvr, that is mv is the linear momentum multiplied with the radius, so mvr. Here v is what, the by the means the velocity which is means the minimum velocity which is required to project the satellite or to set the satellite into the orbit, that is VO we are writing here. So MVOR here. Now MR, if we leave as it is, in place of VO orbital velocity will write root of gm upon r. So the formula will become of the angular velocity, that is root of gmm square r. Now we'll see energy of an orbiting satellite. So energy of orbiting satellite, we know that very well, the mechanical energy or the total mechanical energy you can say is the sum of the potential energy and the kinetic energy. And for the any object which is means we have derived the formula for the potential energy to set the object at any point in the gravitational field, and that will be equal to minus gmm upon r. So here you will see the mechanical energy E is equal to potential energy, that is minus gmm upon r, plus kinetic energy, that is half mvo square. Now E is equal to minus gmm upon r plus half m, and here you can see that the orbital velocity formula we know, VO is equal to root of gm upon r. Here squaring is there, so we'll take the square also, the square and root will be cancelled. Now this is minus gm upon r, and plus this is 1 upon 2 gmm upon r. We'll simplify it, this will come minus half gmm upon r. That means E is what, the total energy is minus half gmm upon r plus h. This small r is r plus h. So this is total mechanical energy and which is minus half GMM upon R plus H. Minus sign is again indicating the force attractive in nature. Next we'll see the binding energy of satellite. Binding energy of satellite is what? The energy required to remove the satellite from its orbit around the earth to infinity is called binding energy of satellite. That means if we are taking out any of the satellite from the orbit, कोई भी सैटेलाइट को हम उसके ऑर्बिट से अगर निकालना चाहते हैं तो वी हैव टू प्रोवाइड सम एनर्जी टू दैट सैटेलाइट टू move out from the orbit, and that energy is called the binding energy. So binding energy is equal to negative value of the total mechanical energy. As just now I told you, the mechanical energy, the formula which we have derived is the negative sign, which is indicating the attractive nature. That means because of this attractive nature or because of the gravitational pull between the satellite and the earth, the earth is provided the centripetal force to the satellite to move on to the same orbit. Okay, so here this is attractive in nature, and now if we want to take out this satellite from the orbit or remove this satellite from the orbit, we require the same energy, and but it is the equal means the energy would be same, but the that is in opposite sign. That means the binding energy is negative of the total mechanical energy. Negative of the total mechanical energy, that means it will become positive here, that is GMM upon 2R or GMM upon 2R plus H. So this would be the binding energy of satellite.